Good afternoon, everyone, and welcome to today's seminar. Just before we begin, I have one important announcement for the viewers of today's webcast. During this webcast, we encourage you to please send your questions through email for the Q&A session after the presentation. And the email is sierrarm@calepa.ca.gov. It's sierrarm@calepa.ca.gov. For today's seminar, it's my pleasure to introduce Dr. Gary Bishop. Dr. Bishop is a research scientist for the Department of Chemistry and Biochemistry at the University of Denver. Since 1987, Dr. Bishop has been employed at the University of Denver, working together with Professor Donald Steadman and his group. This group has specialized in developing spectroscopic instrumentation capable of remotely detecting vehicle exhaust. This equipment has been used to measure light-duty vehicle fleets in more than 21 countries and in more than 30 US locations. In addition, the group has used these instruments to measure heavy-duty diesel trucks, commercial aircraft in London, snowmobiles in Yellowstone National Park, and line haul locomotives in Nebraska. This work has resulted in co-authoring 10 patents and more than 50 peer-reviewed journal publications. Dr. Bishop obtained his PhD degree in biophysical chemistry from the University of Colorado at Boulder in 1986. Please welcome to today's seminar, Dr. Gary Bishop.
Thank you, everybody. It's really a pleasure to be here to talk to you. If you have any questions during the seminar, feel free to interrupt me if you want some clarification or whatever. I don't think that'll throw me off too much. And I will say off of the lead slide, in addition to acknowledging my co-authors, the web address that's listed there is a depository for all of the work that we've done over the last 23 years, including this work. And so at that web address, you will find all of our databases, all of our published papers, most of our presentations, and most of our posters, as well as some of the other projects that we're doing and other information that you can contact me with. I'd also like to say that in the back of the room, for those that are here today, I have some reprints of the journal article that came out of this work that I'm going to talk to you about today, and I would love for you to take a copy with you so that I don't have to take them back home. In addition, there's another reprint of some work that we have done over the last 10 or 12 years that's culminated, sponsored by the Coordinating Research Council, that you're also welcome to take. So to start with, I want to acknowledge the Air Resources Board for the funding support that this project received. We're very appreciative of that. I'd also like to thank Dr. Talzan, who introduced me, who is our supervising officer for the contract. In addition, the university, Mr. Floyd Little from Caltrans Fresno, who was very helpful with some site issues we had there. My wife, who read all of the license plates that's involved in this study. It's a very important part. And Mr. Carlisle, who helped us match those license plates to the California DMV records. So this is just an age-old schematic of what an on-road remote sensor kind of looks like, and I'll show some better pictures here in a minute. But most of the time, our sensor works on a single lane, on individual vehicles, and then we make those measurements as those vehicles drive by under whatever the operating conditions are present at the site that we're working at. To give you a little background in terms of the history of vehicle remote sensing, it was actually, to our knowledge, conceived here at the Air Resources Board. This was something that was totally unknown to us at the time that we started designing a remote sensor in 1987. In fact, Don didn't find out about this till he went to a meeting, I want to say in the early 90s, and somebody that was familiar with the work brought this up to him. But there was actually a report to CARB in 1973 from Hosazaki, Wood, and Kemp of their attempt to build a sensor, which they did build. It was called Remove. It was originally envisioned to measure COHC and NO. It was a ratio device in the same vein that ours was a ratio device, albeit it was smaller, it was battery powered, and it was driven by an analog computer. They had 3 little analog meters that gave readings after the cars went by. It worked sometimes for CO and HC. And as I've highlighted here, what I think was one of the more important outcomes of this work was that it was never published anywhere except in an ARB report. And in this day and age with the internet, that's not as big a deal as it was 40 years ago. But because of that, the work was somewhat inaccessible and eventually became unknown to most of the people who are out there. It's fascinating to look at the report because many of the concepts of drive-through emissions testing, of drive-by signs, of high emitter detection, of clean screening are talked about in this report. And you know, when I read it, it was like, gosh, we really didn't invent a whole lot of stuff here. It's just that we never knew this existed. So in terms of the public literature, 1983, there's a paper by Dr. Cheney that was an associate of Don's who had a high-speed CO instrument that was not quite what they wanted it to be for doing ambient CO monitoring, but Don convinced Cheney to set the thing beside a road and see if he could see individual cars driving by. And he could, and so he published this in the Journal of Air Pollution Control Association and opened the door for Don's original ideas of doing a remote sensor. And that's where I come in. I started working with Don in 1987, and based off of his ideas, we successfully demonstrated that summer a device that we coined the Fuel Efficiency Automobile Test. And at this time, this instrument, it only measured carbon monoxide and carbon dioxide, and it was funded from a grant from the Colorado Office of Energy Conservation. And the concept was that we would find high-emitting CO cars on the road, and we would effect some sort of repair in those vehicles, and they would get better gas mileage, and thus you would save fuel. And so that's where the fuel acronym came from. The detectors were liquid nitrogen cooled, which scared a lot of people, especially political types. But it worked surprisingly well. And I will say this, the biggest difference between that 87 instrument and the 1973 instrument was our original instrument has an across-the-road reference beam. And the major shortcoming of the Hosazaki instrument was that they did not have an across-the-road reference beam. They note this in the report that most likely is the reason that their instrument had difficulties with accuracy in particular. But that's one of the big differences, and that we were fortunately 15 years later and digital computers were a lot more advanced and allowed us to do a lot more computational-wise that they were not privileged to doing. So just some additional things. 1989, General Motors developed their own on-road sensor and demonstrated it. It was very similar to our device. In 1990, we put out what we called our 3000 instrument. We got rid of the liquid nitrogen cooled detectors. We went to more species. We went to a smaller, lighter instrument. And in fact, this instrument, this 3000 instrument, forms the basis of the instrument that I used to do the data collection in this project. 1991, Hughes Aircraft demonstrated an instrument that used an FTIR. It was not fast enough and had some other shortcomings and didn't go much beyond a research phase. In 1994, we added non-dispersive UV spectroscopy to our 3000 instrument to measure NO for the first time. And in 1997, we upgraded that to a dispersive UV spectrometer for NO. The non-dispersive UV device had interferences with aromatic hydrocarbons that were that affected its precision and accuracy, and so we went to a dispersive unit. And then in 2005, we actually put two spectrometers on the instrument, and it opened up the ability for us to not only measure NO, but to also measure SO2, ammonia, and NO2, and those are most of the species that I'm going to talk to you today about. But let me show you what the instrument looks like so you get a feel for what it looks like. And these are pictures from San Jose. There's a dual beam light source that emits both infrared energy and ultraviolet light in a single beam. The IR is emitted from just a carbide, a hot carbide igniter that they actually sell for Maytag clothes dryers. But it's very hot, it's very robust, and they're very cheap. And then we use a xenon arc lamp to generate the UV signal. And in this picture, you'll also see the speed and acceleration bars that are sitting to the left of the source. This picture has everything that's in the previous picture. It's just the source is kind of small out in the corner, but this gives you an idea of what the instrument looks like set up on the road. There's the FEET 3000 detector unit that I talked about. It only detects the species in the infrared wavelength. The UV spectrometers are stacked on top of each other behind the box, right here. The top one, it turns out, in this setup measures NO2, and the bottom one measures NO, SO2, and ammonia. And then you can see the speed bars, and we have a calibration cylinder that's laying there beside it on the road. To give you a better idea of how we deal with dual wavelengths, this is an exploded view of a single spectrometer and the FEET 3000 detector. The red line represents the infrared radiation that's coming into the collection mirror, and the blue line represents the ultraviolet. And of course, they're not separate when they come into the instrument. They're co-located on top of each other. But they come in, they hit the collection mirror, and they are focused down onto a dichroic beam splitter that is transparent in the IR, but reflective in the UV. And so we also have one of these beam splitters on the source side that puts the beams together. Here we take them apart. So the infrared gets focused down through this beam splitter and goes onto the 4 detectors that you can see there on the left: COHC, hydrocarbons, COHC, CO2, and the reference. But the UV is directed across and focused down onto a quartz fiber that then takes that light into the spectrometers. With the dual spectrometers, that quartz fiber is bundled at one end and then is split into 2 separate fibers at the exit end. And we put one fiber into the NO2 monochromator, and we put one fiber into the NO, SO2, and ammonia fiber. The spectrometers are just the standard grading monochromator. We actually manufactured these because in the mid to late 90s we couldn't purchase a spectrometer that was capable of doing 10 millisecond time resolution, and so we actually manufactured these ourselves, but I'm sure today you could probably go out and buy one that would do this. But the instrument itself, and this takes a little bit of getting used to, really doesn't measure anything. Actually, what it does is it compares the gas ratios it sees in the calibration cylinder with the gas ratios that it sees from the vehicles driving by. And it's really just a simplistic comparator. Yeah, there's a lot of complicated stuff going on in terms of converting light into electrical signals and having a computer monitor those. But basically what we do is we set the instrument up on the side of the road, we take out the cal bottle, it has some ratio of CO to CO2 in it, we puff the bottle into the machine, and the machine says that's a 1.2. And so we know that the bottle, it's 1, but the machine says it's 1.2. So anytime a car drives by that the machine says is a 1.2, we turn into a 1. And that's how the measurement is captured, and that's how the calibration is done. Everything is just compared to whatever the ratios are in the bottle. And we do that for each of the gases that we measure. So each instrument will have however many different bottles that we need for all the different species that we have that we are measuring. But everything is ratioed to CO2. And because of that, the ratios, because they're ratioed to CO2, they're actually a fuel-specific measurement. So every species that we measure is related to how much fuel the car is being burned at the time that it's being measured. And so typically, and you'll see later on the slides, we report things in grams of pollutant per kilogram of fuel. And that's directly derived from the ratios that we measure from the cars as they go by on the road. So if you look, these are just IR signals, but I'll show you how this process takes place. So here are the signals, and these happen to be voltages, from the 4 detectors in the 3000 detector for the IR components. So the black line is the reference, the green line is hydrocarbons, the red triangles are CO, and the blue dots are CO2. And so this is a half a second of 10 millisecond average data behind a car that drove by our instrument. And you can see the CO2 line wiggles up and down, and that's the plume rolling by through the beam. So we end up capturing these 50 data points for a half second behind the car, and we have each of these. And there's several ratio steps, but one of the most important ones is all of these voltages are ratioed to the reference. And that takes care of any issues that we may have with heat coming off the road, of body parts getting into the beam when we didn't expect them. If the reference sees something, it's not a gas. And we want to make sure that that doesn't show up as a signal in a gas channel, because obviously it was something other than a gas. So the reference is, and that's how the reference is used. So we take those readings and we actually turn them into pseudo concentrations. And what I say pseudo is when a car drives by our instrument, we know typically how much absorption we see from that. But we never know, Tao, could you get me a cup of water? We never know whether we get an intersection with the plume that has a very large cross-section or one that has a very narrow cross-section. The advantage to the ratios is that we don't need to know because the ratios are independent of path. But it's important in the sense that these concentrations ultimately, individually, are path length dependent. And so the percent in 8 centimeters that I've labeled on the left and the right side of the graph here just indicate that these would be the concentrations we would have seen from this car if all of the exhaust gas had been captured and put into a cell that had an 8 centimeter path length. And so that's what the 8 centimeters here. And so now that I've turned these into concentrations, you can see that while the HC line previously looked rather flat, you can see that it wiggles along with the CO and the CO2 in the same manner, but with more noise. And I will point that out. The HC channel has the highest noise channel. So we take these pseudo concentrations and then we ratio them to each other. And this is the actual measurement and the ratio of that car. So you can see that the red triangles have a slope of 0.41, CO to CO2, and that translates roughly into about 550 grams of CO per kilogram of fuel. This is a very high emitting CO car. In contrast, the HC reading has a slope of 6.7 times 10 to the minus third, and that translates into approximately a grams of HC per kilogram of 14. These ratios are the measurements that we take off of each car that goes by, and we do this for each species of the gas. And as I said, these ratios are scaled according to how the instrument reads the ratios in the calibration bottles. For the UV species, we don't have volts. We actually have absorption spectrums. And these are just some examples taken out of the spectrometers that we have of what the NO, the SO2, and the ammonia spectrums look like in the UV regions that we're sampling for. Each car, if we're doing a half second of measurement, will have 50 spectra taken off of each of the spectrometers. Now, of course, I've got the spectra separated here, if a vehicle has all of these species at the same time, these spectra will be right on top of one another. And we use a classical least squares K-matrix approach to solving the concentrations for these species. And then here's what an NO2 spectrum looks like from the other spectrometer. You can see that the NO, the SO2, and the ammonia are in the very deep UV between 200 and 226. The NO2 spectrum is up in the 440 region. And there again, that's the other reason for separate spectrometers, is we can't cover that large of a spectral range, and so we separate that out. Each car we measure, we take a picture of the back of the car when the measurement's completed. We also record the speed and the acceleration. The numbers at the bottom of the graph correspond to CO, HC, and NO and CO2 concentrations for this car. Again, these are concentrations if you could run behind the car with a standard garage analyzer that you would get. This has been solved using the combustion equations from the ratios that we measure. And then we read the license plates for each of the vehicles that we measure, and then we match those plates against the state vehicle records. And that's the most important part of the information. The measurements are important, but without the vehicle information, they're really not very useful. They were very useful in the beginning when nobody had ever done this before. It was sort of novel that we could go out and make these measurements. But if you want to do any research and you want to ask questions about the vehicle fleet, you've got to know makes and models and things like that. And those are the important information that we get from the vehicle records.
I want to point out that we blanked out the plates.
Oh, yeah. People always ask about license plates, and one of the things that people don't realize is that license plates are public property. You don't own your license plate, the state does. And so while it gets into this privacy question of should you be able to read my license plate, since you don't own your plate, it's not really a privacy issue. But I will say this: we only get vehicle-specific information. We don't get names and addresses or any of that stuff now. 20 years ago we did, but now we don't. And we've never included any personal information in any of our databases that are on the website, but you will have, the license plate is included. And so if you have a car in San Jose, Fresno, thank you, or West LA, you can always download the database and see if your plate's in there. As I said, for this project, we had 3 sampling sites. The top picture there on the left is from San Jose, Fresno, and then West Los Angeles off of La Brea Boulevard. All of the field sampling was done in March of 2008. I manned the instrument in San Jose and Fresno, and Don manned the instrument in West Los Angeles. The San Jose site was at northbound I-280 to northbound I-880. We were there in the first week of March. It was a lovely break from Colorado. I was able to wear shorts and just sort of hang out and enjoy the sunshine. We attempted roughly 31,000 measurements, and in the database, after valid gas measurements, after being able to read the license plates, after being able to match it to the state DMV records, we ended up with a database from San Jose that has roughly 25,000 vehicles in it. We didn't choose the site in San Jose just sort of at random. This site had actually been used in 1999 to make some similar measurements, but without the additional species of NO2, SO2, and ammonia. So we had COHC and NO. And here are the historical comparisons for that site between those 2 measurements in 1999 and 2008. And roughly you can see that CO and HC have gone down around 70% in those intervening 9 years. And NO, not NOx, but NO has decreased about 40% at that site. First time we'd been to Fresno. We were located on a ramp in Fresno that went from northbound US 41 to northbound US 180. I spent a week in Fresno. Only had to do 4 days in San Jose and ended up with 25,000 cars. You can see I spent a week in Fresno and was just scratching and clawing just to get into the low teens. So we had almost a little over 13,000 measurements in Fresno. A different site than in San Jose. This was a curved uphill ramp, and because the traffic's so light, the driving patterns tended to be sometimes nonsensical. I had several people just drive up and stop and look around. And you can do that. In San Jose, if you tried to do that, you'd have been run over and killed. So we had no previous data in Fresno to compare. And then the final site was the West LA site from southbound La Brea Boulevard to eastbound I-10, just south of Hollywood. And we've been using this site since 1999. We actually have 5 data sets in addition to this one from this data site. This data site, if you want to take one of the papers in the back that's the decade of on-road emission measurements, this site is part of that paper. It was sponsored by the Coordinating Research Council as one of our revolving sites where we went to back year after year at the same time of the year to take multiple measurements. Don worked here. We got almost 18,000 measurements, matched measurements at this site. And here's the historical comparison, 1999 to 2008, for the regulated emissions that we have. And you can see it's a very similar picture to what we see in San Jose. The CO reduction is a little bit larger. The HC measurements, they're all just a tad bit larger. But statistically, they're probably identical. And we've seen this, if you look at the decade paper, we see large reductions in these 3 pollutants all across the U.S. wherever we've been. And this is not anything new or different, but it is something that we've got some extra measurements here at West LA and we see a similar pattern. In addition, I made some comparisons to some work that Dave Parrish has published. He used ambient monitors to look at CO to NOx ratios in the South Coast Air Basin over about a 10-year period. He segregated his data to just the morning rush hour. So his ambient ratio measurements that I plotted here are just from the 6 to 9 or 9:30 time slot. And he did this to try to limit diesel emissions. I didn't have those types of restrictions in the sense that California has one of the lower sort of light-duty diesel concentrations of any of the other states. And with heavy duties, with the elevated exhaust, we don't measure them with the ground level instrument. So I used all of my day's data to plot this companion graph. And of course, we've only measured NO2 this last year in 2008. So what I've plotted here for the remote sensing data is just the CO to the NO ratio. But that constitutes 98 or 99% of the NOx. But what you can see is that, and tabulated down at the bottom, are the reduction rates for the Parrish data from LA, and in that paper he also had some data from Nashville that he published. In the ambient data, Dave sees something on the order of 6% a year, plus or minus a 0.5% reduction. And you can see the San Jose data, where I only have 2 points, that reduction rate is around 7. They're both San Jose and West LA see about a 7% per year reduction from the remote sensing data. And so there's quite good agreement to some of the other literature data just from the ambient data alone. And one of the things, at least for the 6 to 9:30 p.m. time slot, it confirms some of Dave's suspicions that the light-duty fleet is driving the reductions that he sees in the ambient data set, and that stationary sources are a minor contribution to this. So here, just to give you one slide, could compare all the regulated emissions from the 3 sites. And NO2 is included in this slide. It's the black bars. You can just see it's a very small contribution since the large majority of these vehicles are gasoline. It makes up just a tiny fraction of the total NOx from the light-duty fleet. What's not included in this slide is there are age differences between these fleets, and those, of course, have great impacts on the height of these bars. And then here are the specialty species that we've added. ammonia, SO2, and just NO2. So I've separated out NO2 and I've expanded it so you can see actually what the NO2 readings are for each of these sites. And I'll make comments on the NO2 a little bit later. I will show at the bottom of this graph I've included the available literature values for ammonia that have been published from various fleets. Rob Harley's group has done 2 measurements of ammonia in the Caldecott Tunnel. Our group had some previous measurements in Denver and Tulsa on ammonia. And then Baum et al. Has some measurements from the late 90s for LA. And basically what you see is that the measurements that we made in San Jose and Fresno fall sort of in the middles of all what the literature values are reported. The ammonia values at the West LA site are the highest that have been reported. And when I get into more detail of that later, I think there's some possible explanations for why that is. The other thing I'll point out in the fleets that we've measured is that there is still a lot of low-hanging emission fruit out there if you're willing to look for it and go get it. What these graphs are is if you rank order the emissions measurements at each of the sites and take just the top 1%, these are the fraction of emissions that top 1% is responsible for. And you can see that they're quite large. And one of the things that I've been interested in that I'm going to maybe look into a little more this summer, technically speaking, the fleets are getting more skewed each year. These 1% numbers are getting larger each year because the emissions of the majority of the fleet are being driven so low. Since I&M, or an inspection and maintenance program, is supposed to deal with the dirtiest of the dirty cars, to me it logically tends that the benefit in terms of percentages from an I&M program should be increasing each year because it's easier to find these dirtier cars, and if you clean one of them up, they are a larger percentage of the problem. But if you look at the mobile and moves computer models over the last 10 or 15 years, their I&M percentage benefits get smaller every year. And to me, that's counterintuitive, and I'm not quite sure what the reason for that. I make no claims that I know anything about MFACT, and I don't know what MFACT does in terms of percent benefit from an I&M program, but I thought I'd throw that out there that somebody might be interested in looking at it. And the other thing that I'll point out is that because these distributions are so skewed, if you do some type of an emission study and you miss the one car that's responsible for a large portion of the emissions, and then you try to make a model or an inventory or make some claims off of that study, you can be off by quite a large percent if you miss the wrong car. So just thought I'd throw that in there. But the other thing that I'll point out is that if you do that 1% calculation each day at each site, it wiggles around. It's not the same cars every day. And that's because, as this graph shows, as average emissions go up, the variability increases enormously. And many of these broken cars are very variable. And I'll also point out, if you noticed, the much larger HC fraction at the West LA site compared to the other two sites. There are a couple of VW bugs that are really two-stroke snowmobiles in disguise. And that's one of the reasons the HC emissions are so high at that site. But the other thing that I'll throw out, when you get these data sets, they're nice and large and they have lots of numbers and there's lots of things you can do with this. And this isn't an emission exercise, but it's one that I found quite interesting. This is the fleet fraction by model year for San Jose. And what I'm going to do is I'm going to add on each fleet fraction for each of the 3 sites. But because of the complexity of the bar charts, I'm going to add them one at a time so that I can make the point that I want to say. So far as recessions and new car sales are correlated, you can look at that effect in our data set. And 9/11 happened in the fall of 2001, and we had a medium kind of recession following that. And if you look here at the San Jose fleet fractions, you can see that the fleet fraction for newer vehicles after 2001 went down till about 2003, and then it started to go back up, And by 2006, it was completely recovered. 8 and 7 probably aren't completely populated by this time when we made these measurements. But you can see that by 2006, it looks like it was completely recovered. If you then look at the Fresno data, and the star marking the 2001 model year just for your eye, you can see that the fleet fraction also dropped after 2001 in Fresno, but never went back up. And then if you go to the West LA site, and this is where it really gets busy, concentrate on the blue bars, you can see that the West LA site didn't see the 2001 depression or recession at all. And I'm sure if I were an economist or knew an economist, there's probably all sorts of reasons I could go into zip codes and census data and median incomes and maybe pull out an answer. But I just thought it was an interesting observation and one that I wanted to share. So now I want to switch gears and talk about ammonia, which I think is one of the more interesting species of the new ones that we measured. And this is ammonia emissions in grams of ammonia per kilogram of fuel, plotted by model year for each of the 3 sites. And you can see that San Jose and Fresno, for at least the first 10 or 12 model years, is fairly similar. The difficulty, of course, with the Fresno site is I have a much smaller data set. And after about the first 10 or 12 years, you can see the noise goes up quite a bit. The error bars that are plotted on the Fresno data are calculated using the daily means. So I've got 7 daily means, and I distribute those, and those are standard errors of the mean for each of those model years. And that gives you an idea of what the error bars are on the other data sets as well. They're going to be at least this big, and perhaps maybe sometimes they'll be a little smaller. You can see that the West LA site has the highest ammonia emission rates, and they go up at a steeper rate by model year than they do at San Jose and Fresno. The West LA site is a traffic light controlled on-ramp, and so typically we see much higher acceleration rates there, but also because it's traffic light controlled, you get queuing and you get stop and go driving coming up the ramp until you're finally allowed to drive. And Huai did some work back when he was at Riverside, showing that at least this pattern of deceleration followed by acceleration was a very good driving mode for expressing ammonia. And the LA site is the only site where we have really defined decels ahead of the accels. And so one of the suspicions of why ammonia emission rates there are higher is that perhaps not only do we have aggressive driving from the traffic light, but the catalyst has been prepped a little bit ahead of time, and there's actually perhaps a little more stored hydrogen on the catalyst on the cars in West LA, and so they've just got a larger reservoir to convert NO into ammonia at that site. And that's just speculation. I don't have any hard and fast data to support that. But the other thing that I'll also point out is ammonia is the only pollutant that we've ever measured that goes down after a certain time. All the other ones tend to go up and they'll level out. But ammonia actually goes up, it peaks, and then goes down. And what we know we're seeing there is the ability of the catalyst to reduce compounds wears out over time. And after about 15 or 16 years, the catalyst, the reducing part, starts to age, and it loses its ability to, even if it can store hydrogen, it loses its ability to reduce the NO to ammonia. We see a VSP dependence on ammonia, as you would expect. And this is a graph showing the vehicle-specific power measured at each of the 3 sites, and of course the West LA site with the highest ammonia readings and the highest acceleration rates. We see that a little more defined than we do at either San Jose or Fresno. And I mentioned Huai a minute ago. We thought he published a paper in 2005 with a VSP model. And so we thought we would see what we looked at. Now, Tao didn't publish grams per kilogram, and so we had to estimate his milligrams per mile emissions into grams per kilogram. And Don made some very semi-elegant conversions to Tao's model. And so the line is just an approximation. But the things that I'll point out is that we do see an inflection point sort of between 20 and 30 kilowatts per ton on both the on-road data and TAL's model. And the other thing that I'll point out is that our data are fleet averages, whereas TAL developed his model based off of some very individual and often much newer vehicles than what we have been looking at. The other thing too is our data, once you get out of past 35 kilowatts per ton, there aren't a lot of data points in some of these points, especially the at West LA. There's 3, 9, 6. I probably shouldn't have had the license to plot them, but I did anyway. So the other thing that I'll point out is that we've always been accused of manipulating our data. I don't know how many times we've been accused of manipulating data. I have manipulated data to make these graphs. I have scaled the left axis and the right axis so that the grams per kilogram of ammonia and the grams per kilogram of NOx from Fresno and San Jose overlap. So I forced that overlap just based on the scales that I picked on the other side. But I did that to show you that both the NOx and the ammonia at those sites are decreasing at the same rates. Now, West LA, what's interesting, and it's a little difficult to see, but if you look right in here, at the West LA site, the NOx emissions stay down longer than they do at San Jose and Fresno. It's very small, but they are flatter for a couple of extra model years on average than at the San Jose and Fresno sites. And my theory on that is that NOx emissions at the West LA site are being suppressed by the ammonia emissions. And so ammonia is much higher at the West LA site, and it's taking NOx away and being emitted as ammonia. And so you don't see the similar overlap at the West LA site that you do at the other sites. Now I'm going to walk you through this graph too. There's a lot on here. The green triangles and the lines are total fixed nitrogen, and they're defined by the right axis. So just focus on the green triangles and the line right now and forget the blue and the black things. What this shows is that the total fixed nitrogen from the vehicles is going down quite dramatically over the last 20 years. And I usually think of things fixing nitrogen being peanuts, plants, stuff like that. I'm not used to thinking of cars being something that fixes nitrogen, but that's what cars do, at least in the three-way catalyst stage. They now are a very large source of fixed nitrogen in our environments. And that's what the green bars plot here, is the total amount in grams per kilogram of fixed nitrogen. Now, if you look at the blue dots and the bow ties, what that does is it takes each model year and divides up the percentage of that total fixed nitrogen into the two species. And you can see for the early 90s, late 80s, early 90s vehicles, something around 90% of that fixed nitrogen is NOx. And as we go newer, depending on what city you're in, Fresno and San Jose, they cross in the late 90s, and at West LA, they cross a little bit later than that. You can see that in the newer vehicles, the majority of the fixed nitrogen that's being emitted is ammonia. And in fact, in the very newest model years, it's largely ammonia, like, what do you got, 80%, 70%, 40% in San Jose. It's not as skewed. But for new vehicles, most of the fixed nitrogen coming out of the cars is ammonia. So for grins and giggles, we saw a paper in EM that EPA published about a year and a half ago, and they had an ammonia inventory in the paper of 307,000 short terms for the whole nation for a year. And so we would just thought we'd take our mean emissions and just say what if. Okay, our mean emissions represent, every car in America, and you take 380 million gallons of gasoline a day and you do the math, and these are the short ton numbers that you come up with from these mean emissions for those two values. And you can see that the EPA number is much closer to the high end of our numbers than it is to the low end. And we happen to think the West LA site happens to be an extreme case. We don't know that for sure, but we think probably the average ammonia emissions is probably much closer to that 0.49 number than it is to the 0.79 number. I tried to do some background work to find out what the EPA inventory is based off of, but have sort of run into a dead end there, and so I'm not real sure. The paper that they reference the ammonia work just tells how they calculated the number. It doesn't give any sources for the data that they used to base that on. So one of the other species we looked at is sulfur dioxide, and so this is the time that I can be embarrassed, because there should not be a model year dependence on sulfur dioxide from light-duty vehicles as we measure them. And of course, you can see from this graph there's a very nice model year dependence. The black line that is drawn at the bottom is at about 0.03 grams per kilogram of sulfur. And technically, with California's low sulfur fuel, that's the level that all the cars should be putting out, because there's no other sources for sulfur in a car except from the gasoline and the lube oil, and we happen to think that the contribution of sulfur from the lube oil is very small. And so all the cars should really be putting out somewhere around 0.03 grams per kilogram. And you can see that for about the first 8 or 9 model years that seems to be the case. But after that, we get a nice strong model year dependence. And we know that some of that is interferences from aromatic hydrocarbons. And this is just all of the data from Fresno. And it's just a scatter plot of grams of HC per kilogram on the x-axis versus grams of SO2 on the y-axis. And you can see out here to the right that as the HC goes up, the SO2 goes up. And so there is some interference from hydrocarbons. The difficulty is that if we subtract out the hydrocarbons from our data, it doesn't get rid of all of the model year dependence. It gets rid of some of it, but it doesn't get rid of all of it. And so there's more to the story than just hydrocarbons. Now, certainly as cars get older, they're going to burn more lube oil, and so there is some additional sources of sulfur in these older cars that we could be picking up. But this is a story that's yet to be fully written, and we're still talking about and doing some work on this. But sulfur is really, or SO2 was really an issue that we brought to the table because we were looking for misfueling. And so if you look at the very highest points on here, you can see that the SO2 goes up to around 4 grams per kilogram that we're dealing with in Fresno. This is some data from heavy-duty diesel vehicles we took at the port of LA 3 years ago. And it was during the time when diesel fuel had gotten over $4 a gallon in California. And you can see that we measured some diesel trucks that had SO2 emissions that were much higher than 4 grams per kilogram. And the large triangles are repeat measurements on the same vehicle. So, for example, the 1984 vehicle we measured 4 times, and you can see he had a range of emissions depending on the day we measured him. And then there's a 1992 vehicle that we got 3 measurements on, all of which were very high. And I just show this so that even though the interference that we see in the SO2 in cars is large, it's not near as large as some of the numbers we've seen from trucks that we have a strong belief that they're being misfueled, either from some sort of Mexican fuel perhaps, or even some sort of marine fuel that they have access to in the port area. I will say the last 2 years that we've been at the port, we no longer see these high SO2 trucks anymore. And in many instances, many of these trucks have already been banned from the port, so they're not there, they're somewhere else. The last species that I'll talk about is NO2. And working for Don, sometimes you begin to feel like that you're just lucky. And sometimes it's better to be lucky than to be good. We were at the Fresno ramp, and like I said, it didn't have a lot of cars. And I get antsy when I'm sitting out there, and I get 100 cars an hour. But when we got back and we started looking at the data, Allison Peddle, who's one of the co-authors, was the graduate student that was putting us in a thesis, and she brought me this graph without the line, just had the points. And here's this point in 2007 in Fresno that's way up on the thing. And of course, when a graduate student brings you a graph where there's only one point that's completely out of joint, you look at them and say, this can't be right. You've obviously done something wrong. Take it back and do it again. And she did. And she came back and she said, no, that point is supposed to be there. So we start looking. And sure enough, you do a rank order on the NO2 emissions, we end up with these really high readings from just 2007 vehicles. And I look at the VINs, and the VINs are all the same, with the exception of the last 6 digits. And that just sort of catches your eye. So we looked into this. We happened to be on the ramp in Fresno that the ambulance fleet that served the downtown medical center used for its return loop. And the ambulance company, and I don't remember the name, I think it's in the report perhaps, had just replaced their entire ambulance fleet with a fleet of 2007 Dodge Sprinter diesel truck chassis that included a diesel particulate filter with an oxidation catalyst for regeneration. And we had 52 measurements, of which 31 ambulances comprised those 52 measurements. And here's what the comparison looks like. Now this is just 2007 data from Fresno. One of the weaknesses of this data set is that we did not get from the state fuel type. And so I would have loved to have just distributed fuel type over the entire data set, but I had to decode fuel type by hand. And so we just did the 2007 model years. But this gives you an idea of what those comparisons look like. And a couple of things I'll point out. The Sprinters with the diesel particulate filters have smoke emissions that are statistically the same as gasoline vehicles, and that's good. I mean, that's what the particulate filter is supposed to do. But you can see, if you look at the middle, over here on the NO2, their NO2 is about 5 or 6 times what it is for all the other diesels. And of course, it's hugely greater than it is for the gasoline engines. And when you look at this on a mass ratio, you can see that about 60% of the mass of the NOx that these Sprinters are emitting is NO2. And it's important, at least at this point. I called the ambulance company, and they told me their ambulances average 50,000 miles a year. So even though this ambulance fleet is a terrible small fraction of the total Fresno fleet, they contribute a significant portion of the NO2 emissions in Fresno. And the good news is these ambulances will probably only be there for 3 or 4 years, and then they're gone, because I'm sure they wear them out and trade them in. But we hope, of course, that when 2010 compliant diesel engines start filtering into the fleet in large enough values, the NOx emissions aren't going to be important. But so far as that doesn't happen, as more of these DPF-equipped pre-2010 compliant engines come into the thing, if they really are putting out this much NO2, it has really interesting air quality ramifications for freeways, because for fresh emissions, that NO to NO2 ratio in terms of ozone is really important, because it dictates not only how much gets titrated from what may have left over from the day before, but how soon you can start making new ozone. And with so much NO2, if that fraction really does change, it really changes the ozone dynamics around freeways. And maybe that's a good thing. People always say we're supposed to stew in our own juices, and typically there is no ozone on freeways, but maybe in the future there will be. Nobody quite knows. So in conclusion, and I'll let you read these, we have 3 data sets, close to 50,000 measurements. it's the largest ammonia, SO2, and NO2 data set in the world for individual vehicle measurements. And I'm sure I've only scratched the surface in terms of types of analysis that you can do with it. And so I always encourage other people to go to the website. The databases are there. You can download them. You can use them any way you see fit. We're always available to answer questions if you have any questions about them. And so that those on the webcast will know, there are 4 slides that contain most of the literature references that I have used in preparing the data comparisons and whatnot. So I thank you for your time. It's an honor for me to be able to present this work, and if you have any questions, I'll be glad to do my best to try to answer them.
Question? Thank you for a great presentation, Gary. Can you address, and I think you hinted to this a bit, the activity dependence, the vehicle operation dependence on the measurements, because you're constrained to the on-ramp. And I know you do some of this by normalizing with CO2, but can you expand on that?
In terms of dependence, do you mean emission levels, or do you mean in actually being able to make the measurement?
All of the above.
Okay. Insofar as making the measurement is concerned, vehicle operation, we're highly dependent on the vehicle burning fuel. And so if you end up in these situations where you have a lot of off-foot motoring, we are going to have a much higher or much lower capture rate because there's just not any exhaust there to measure. And so we typically try to find uphill locations so that we force the driver to drive the car. We can deal with flats, but high-speed downhills are just a loser for us from the standpoint of there's just not enough exhaust for us to see. It took me a few years to appreciate the fact of making a 10 millisecond measurement is hard to do, because when Don told me how to do it and we did it, I just thought, well, that's not that hard. But it really is difficult to make a time-resolved resolution or measurement at the speeds that we need to go before the plume completely dissipates. And of course, this is dependent on the size of the engine of the vehicle as well. We will not have the same capture rate on small 4-cylinder engines that we do on big V8s. And it again goes back to the fuel issue. I mean, there's just more exhaust behind a big V8. We can mitigate a lot of those things, of course, by having an uphill driving site. As long as we force them to drive, that helps out. Other things about vehicle driving, typically wind and vehicle speed aren't real issues other than deflecting the plume from the measurement beam. If the plume doesn't cross the measurement beam, of course, we can't measure it. So if you're measuring cars in a location where the wind speed directly from behind is larger than the speed of the car, well, the exhaust is going out the front and we won't measure it. That's an extreme case, of course. So there are always biases in any measurement method, and certainly a bias in some of our averages has to do with, do we really capture enough of the small engines all the time at all the sites? And that's something that certainly you can do with the data in terms of comparing fleet fractions based on engine size. It's not something that I've done with this, but it's something that you could do to look at. Oh, we have a machine that'll measure motorcycles too, but it's much more confined than the vehicle's instrument. It's confined to a path length of 6 feet? 7 foot 6. But it's a multi-pass, so the beam goes up off the ground about 3 feet. So we can look at small 2-cycle engine motorbikes as long as you make them drive through it. Okay.
We've got a question from the email. If you could read it first so that audience can.
For UV remote sensing for SO2, actually, approximately 290 nanometer UV region is the best area to measure SO2. There's very little interference from HC. In the recent market, CCD or DPA UV spectrometer covers 200 to 600 nanometers, only costs several $1,000s. By the way, what's your UV spectral resolution? It looks like 1 nanometer or higher. Remind, what? 0.3 nanometers is our spectral resolution. If you can lower down the spectral resolution to 0.4 nanometers, SO2 should be very easy to measure, and you might get some aromatic HC like BTX, and we can do that. The spectral region, the diode array that we use is a 256 diode array from Hamamatsu, and the spectral region for SO2 was chosen because it coincides also with ammonia and NO, and so we tried to do all three at once. I will say that I am less, what's the right word, concerned about some of the SO2 interferences from the standpoint that because of all the sulfur being taken out of the fuels in the U.S., SO2 is not very interesting anymore. Unless you get into the situations along borders and whatnot, or tax issues where you have misfueling. And I don't want to flippantly push that question aside, but that's kind of the way I've been looking at it lately. And I haven't energetically looked into some of the SO2 interferences as much as that. But yeah, we do see BTX. I can blow toluene into the instrument and it goes nuts. So yeah, we do see the aromatic hydrocarbons in that region. And thanks for the comment.
We did a toluene-specific measurement on snowmobiles.
Yes.
But they're
Yeah, they're two strokes. If you look at some of our snowmobile work on the site, you will see some toluene to HC correlations that we measured on two-stroke snowmobiles. But there we get the benefit of vast quantities of raw gasoline to look at, so it was easy.
Huai from ARB. Excellent presentation, Gary. I have a few comments. The first one actually relate to one of your statements talking about the 1% fleet contribute a lot of, majority of the pollutants. You mentioned, the smoke check might be a good solution for this, but just to give you some suggestions that in California, it's not only the policy, how we're going to replace those high emitters, but also there is a difficulty for smoke check program actually bring in those high emitters because some vehicles won't even enter the smoke check program. So there's a limitation over there.
But that comes down to political will. Right, and I realize, you have to deal with that, but what I'm saying is the old phrase, where there's a will, there's a way, applies.
Correct, there's a lot of agencies.
But you have to have the political will, and yes, you're going to catch an awful lot of flack.
Yes.
So that's why it hasn't happened.
A lot of public agency right now is pushing forward, trying to bring in those high emitters, either replace or scrap or do something on them. So there is effort, but there is some.
Oh, I understand. No, I know. I'm just trying to remind people that there are still emissions out there to be harvested. We haven't gotten rid of them all.
Okay, my next comment is based on your discussion talking about the age of the catalyst impact to the ammonia emissions. This one, right. Actually, I have a little bit different interpretation on this reduction just based on the modern years. I believe the engine control technology contribute more impact to this reduction rather than the age of the catalyst.
Okay.
Because if you look at the two more slides, the big comparison, yeah, this one. If you recall in my paper, there's actually 3 regression lines, not only one, with latest control technology, actually the slope is going to be lower and lower.
Yes.
So that's the trend. Also relate to this slides, you mentioned that the Fresno and the San Jose said they are not the stop and go location. So you basically
directly.
You basically missing. This is kind of limitation for this remote sensing, which is you cannot capture the most efficient driving mode for ammonia emissions. That's part of the reason you won't see huge ammonia emissions from your plot. And for the West LA, because stop and go, they do give you the opportunity to capture those high emission events. Okay, that's my comments.
Thank you. I appreciate it. I enjoyed your papers.
Hi, Gary. Thanks for coming all the way out and giving a very nice seminar. I have a number of questions. I'll ask them one at a time so you won't get immediately overwhelmed. The first one is on the slide you showed just before on there's still low-hanging emissions. I'm wondering if the percentages you have in there take into account the activity of the various vehicles, or
No.
whether it's just based on the emission
It's
factor.
just based on the total measurements.
All right.
So you add up the total measurements and then you divide them by what the top 1% contributed.
Right.
And so there are repeats, and I didn't unique the vehicles or anything like that. And I tried to say that this is the measurement, 1% of the measurements.
Okay, thank you. And then in your Fresno 2007 model year fleet emissions, the NO2 to NOx ratio for the Sprinters, how heavy were the Sprinters? Were they medium heavy duties? Were they
I'm sure
heavy
they're
duty?
probably classified as a medium heavy duty, but I don't know that for sure. They were in my VIN book, which was the passenger car VIN book. So they're still considered some sort of passenger type vehicle. They're not in the heavy duty or the commercial VIN book.
Okay.
You realize they're a standard Sprinter, but they've had all this ambulance
Yeah.
added to them, so they're probably overweight.
They're probably heavier than what the vans are that are out on the road. And they do make a gasoline version of this Sprinter as well as a diesel, but these were the diesels.
And then finally, staying on the NO2 to NOx ratio, I know that you've done remote sensing at the ports as well.
Yes.
I was wondering if you have any updates on what the ratio has been lately at those ports, or when you were last out there.
The newest model years at Peralta are in the 50 to 60% range on a mass basis. Now, we just took new data in May, which would be the first year if there are any SCRs in the system, they would show up, and that data is still I'm still reading the plates, and we haven't done any plate matching, and so it'll be the fall before I know model years in terms of what the emissions were. Oh, the other thing I'll make a point that just occurred to me about the 1% slide. These are measurements, but no matter how you slice up this database, these statistics go across all sorts of things. So even if I uniqued these vehicles and just did it for unique vehicles, you'd see almost exactly the same distribution. If you sliced it up a slightly different way, you would see almost exactly, the numbers would change a little bit, but you still see this extremely skewed distribution, no matter how you would carve up and bend the data.
You might comment on the hydrocarbon cars in West LA, which we looked at.
Oh, there was a couple of old VW bugs that were putting out more than the average snowmobile we saw in Yellowstone.
One of them,
I'm sure one did not have a smog check record, and one had a smog check record that ended in 1999, which is probably when it became exempt.
Right. And one last question. What was the age distribution of the trucks that you mentioned that had the 50 to 60 and NO2 to NOx ratio?
These are the 08 and 09 model year trucks and 010. So these are the newest ones. These are the ones that have diesel particulate filters.
And within the range you stated, was there a difference by model year?
Yes. I don't know if I have it up my sleeve. I don't think so. If you go to give me your card, I will send you my CRC talk from this year, because that talk had that NO2 slide in it. I didn't do the ratio, but I plotted grams of NO2 per kilogram by model year for each of the two sites, and you can see there's a break point starting with 2008 chassis model years.
Thank you.
And so, hopefully we'll see that just sort of die starting in 010 or 011, and I don't know when they're going to phase it.
Hi. In the case where you saw the high NO2 fraction in the emissions, do you have a sense of what the VOC to NOx ratio would be sort of in the plume and in the background? Did you have any measurements of that?
Well, it'd be very small, right, because they're a diesel. So, we measured HC emissions on those vehicles. I don't know off the top of my head what those averages would be, but that VOC to NOx ratio would be very small.
Is that true for even if cars aren't coming by as well, like in the background?
Oh,
I'm just wondering about both. So
one of the things that we do is we normalize, when we make a measurement behind the car, and I didn't try to go into this because it gets a little confusing. We measure the air in front of the car and then the air behind the car. And we normalize the data behind the car from the data that we get in front of the car to try to account for some of the background stuff. But with HC, we have such poor signal to noise that we can't see we can't see any HC emissions in terms of the background or that's left over very long. So there isn't a carryover issue in terms of measuring the HC emissions.
okay, thanks.
Gary, if you just go to the site slides, you've got the slide of the San Jose site.
Yeah, okay.
You actually have the HC to NOx ratios on those slides.
For the averages.
Yeah, for the averages, so you can actually get the, there you go. And what do you got? HC at 2.9 and NOx at 0.14.
But largely that's dominated by the gasoline cars.
Well, actually, that's HC and NO at 2.9 each, isn't it? They're 1-to-1 by mass. Except that's NO, so you have to mass it as NO2, so it's really...
It's really 3.6 or something.
Yeah.
3.6 and 0.14, so it's 3.8. So call it 3 over 5 for the fleet.
The other sites too, are they much different?
San Jose has well, and here again, Fresno had the highest HC average because it's got the oldest fleet.
Right.
And it's got the oldest fleet because of that, the fact that there were fewer newer cars sold since 2001 in Fresno. So it's the oldest.
Hi, Gary. On the low-hanging emissions table, what's the age distribution of the high emitters, that top 1%? Do you know?
I can't tell you off the top of my head.
But you had, presumably you had the license plates.
Yeah,
So
it's in the database.
Okay.
I mean, I made this slide on Friday or Thursday and just sort of rank ordered and did the sums, and I didn't. Don wanted me to make this slide, and obviously it's been a favorite.
It has been. Sort of a follow-up on that.
I can guarantee you that it's much older than the average fleet.
Right. Do you happen to know what the registration status is of these vehicles?
No.
That would be another interesting thing to look at.
No. We have, from time to time, run plates through the smog check database just to look, to see. In fact, you did that for the poster, I think, a few years ago. But no, I do not know the registration status. Beyond the fact that that DMV had a current record that they matched the plate to.
And then on the NO2 to NOx ratio, do you have a sense of whether that ratio changes as a function of vehicle operating conditions?
I think it does.
So if
we measured them in a very lightly loaded situation.
Oh, like the locations where you're capturing these vehicles?
In Fresno.
Even though it's a ramp, right?
Right, it was a ramp, but it was a very, if you look at the picture, it's a very large ramp where the elevation is spread out over a large distance. And, what I mean by lightly loaded is that the acceleration rates, don't I have that down there? See the mean acceleration was 0 at Fresno.
And how about Peralta, where you measured the 50 to 60%? Was that?
The trucks.
Yeah, were they?
15 miles an hour, half a mile per hour per second, roughly.
So they were just rolling through this?
No, they're
were they accelerating?
They're accelerating out of the way station back to the highway, coming up a 1.8 degree, I want to say. I've got it in one of the reports. The first year report is on the website, and it has the speeds and accelerations and whatnot.
Right.
But They are not as heavily loaded as we measure at the port as at Peralta, but in large part that's because there's enough time they've gotten into a higher gear when we measure them at Peralta. At the port, we typically measure them in first or second gear.
And do you remember what the NO2 to NOx ratio is at the ports?
You know, what's interesting at the port is that the NO2 emissions level out and are the same for like 08, 09, and 010 trucks at the port. And some of that may have to do with the fact that there's enough natural gas trucks that basically have no NOx. And I haven't dissected that in completely. But typically, the NO2 values on a gram per kilogram are similar, but they're higher at Peralta by model year. But like I said, at the port, there's a big slug of 2009 LNG-powered trucks. And they have low to no NOx, especially the stoichiometric engine one. There's a lean burn engine that has some NO2, but not a whole lot.
Okay, thank you very much, Gary.
Sure.
Good talk.
Gary, one more question. I just noticed that from this slide, you showing the mean speed is like 25. I mean, acceleration is about 0. So back to the comparison slide has the slope, you know. So to me, it's
Yeah, no.
so it's hard to
Fresno is very flat.
yeah. So we talked about this one before. So to me, it's a little bit surprised me. You have some data points that's reached to 50 under VSP, because under that kind of speed and the acceleration, the VSP won't go beyond 30. So that's my understanding. Maybe
Yeah,
we have different.
but if you've ever set out on a ramp today, you get the occasional person that likes to horse around with their car when they can on some of these things, and when they see stuff set up on the side of the road, they give you a full throttle acceleration.
Well, so
What I'm saying is there aren't many points out past 35.
Okay.
I want to say there's less than 20 cars out past 35, with the exception of San Jose.
Okay.
But yeah, you get 40 to 50 VSP with a 25 mile per hour car doing 5 miles per hour per second acceleration.
So that's going to be really aggressive
Well, it is.
behavior.
But there's a lot of those out there, or they're out there.
Like you said, you're so lucky.
Hi, Gary. I have a different question, and just taking advantage of the fact that we have you and Don here. Can you comment on, as you know, PM
Am I gonna get
emissions?
into trouble?
No, absolutely not. PM emissions are important, and remote sensing on PM has seen some development in recent time. Can you address, just for general audience information, where you are with respect to remote sensing and PM measurements?
You know, my feeling, and Don will have a different answer than I'll have. I feel like PM measuring and remote sensing is basically for high emitter detection. We can find high emitters. But you know, you can sit at the weigh station in Peralta and watch the truck drive up the interstate, and you can pick the high emitters out very easily that way and not have to use an instrument at all. So yes, the opacity measurements in the FEAT 3000 instrument is an IR measurement only, and it only works on soot. It does not see white coolant smoke, and it does not see blue oil smoke at all. But it does see black carbon. And so you can find high emitters using it that way. The UV technology that they use in the RSD 4600 instruments sees particulates in all these spectrums, and it appears to be quite good. And in fact, there's a whole report where they did correlations against ETAPS and against dyno studies in West Virginia from a year and a half ago that shows that the UV in the commercial instrument sees different colored smoke quite well and can quantify it much better than we can with the IR channel. But there again, I still think it's a high emitter detection thing.
I think
But I think you can do it with your eyeball. So.
You can, but you have to pay human eyeballs. You have to pay health insurance, and they don't work at night. Remote sensing can
That's
get past
true.
that.
Yes, you could do that.
Having said that, the UV opacity meter study, John Collins was actually the project monitor on that program. There's a very nice report, and what I like to think we showed with that report is that if you do take a commercial remote sensor, which has a deuterium lamp in the UV, and the trouble with measuring opacity by remote sensing is you have no reference, because the reference channel is going to be blocked by the smoke just the same way everything else is going to be blocked. Smoke is going to behave like a bicycle spoke. It's going to lower everything. And so it's actually harder to measure smoke by remote sensing than it is to measure any of the gases, because you have no reference. So you have to be willing to believe that you really do have stable references before and after, and that you know what's going on and all this good stuff. And the advantage of the UV that they have a deuterium lamp which doesn't flicker. Now, when you're doing spectroscopy and you have a complete spectrum every 10 milliseconds, it doesn't matter if one spectrum's half the intensity of the next spectrum, because the absorbance will be the same anyway. The peak will just be a 10% peak on a 50 instead of a 10% peak on a 100. But when you're trying to look for smoke, that 50 and that 100 will look like a factor of 2 reduction at light intensity. So our xenon arc is brighter, gets us better spectra, but is not very good for smoke. Their deuterium lamp is much lower intensity, but it's much better for smoke. So they do a very good number on a UV smoke factor. And what I think the one-line conclusion I'd give you from our ETAPS report is that if you see a smoke factor of 0.13, which is actually 1.3 grams of soot per kilogram of fuel, then that number, if you see that number or above on a DPF-equipped truck, the DPF is 99.5% likely to be broken. There's something wrong with that DPF. So I think we showed that you could find broken DPFs with a UV smoke factor pretty well. And this is a full gravimetric multi-cycle analysis with a little aid of little statistics.
Thank you for coming. I appreciated you being here.
Any other questions?
Okay, let's thank Dr. Bishop again for today's wonderful presentation.
Tal, don't. I mean.